Hello, everyone. Today, we'll be talking about more about recursive definition. So previously, we have seen how to apply recursive defined functions, recursively defined set. Okay, so last time we have seen how to apply string concatenation using basic step and recursive step to describe what is the results of string concatenation. Today, we will see how to calculate the length of strings using recursive definition. Okay, so let's see, for basic step, we can define the length of empty strings, the length will be 0. Okay, so this is the basic step. For recursive step, we can use LWX, okay? So here, W is the string from the string set, sigma star, and W is alphabet from the alphabet set. So we can further separate the string into a complete string W and one alphabet in the end. Okay, so for the recursive step, we can write the length equals to the length of L plus 1, because we know the length of alphabet X, which contribute to length 1 into the total length. So you can see this is a recursive definition, because once we need to calculate the length of WX, we can separate to length of W plus 1. That's the last alphabet. Then we can apply recursive definition for LW again and again until the string will be empty string. Then we separate all alphabet out of this string W. Okay, so maybe we can use a real example to see how we calculate the length of string using this definition. Okay, so for example, our string is what? Okay, ARE. Okay, then when we calculate the length of strings, we can separate ARE to W and X. Okay, so the length of ARE equals the length of AR plus 1. Okay, because we just calculate the alphabet E will contribute 1 to the length of the string ARE. Okay, then we can further separate AR to W and X. Okay, so that will be the length of A plus 1. This one means R, and the previous one, okay, so that will be length of A plus 2. Okay, so in the last step, we will have length of lambda plus 1 and plus 1 and plus 1. So length of lambda equals 0. So in the end, we will get the length of the string ARE to be 3. Okay, that's how we apply recursive definition to calculate the length of a particular string ARE. Next, we will see the definition of well-formed formula. This helps us to connect to our previous section, propositional function. Okay, so let's see, we can define the set of well-formed formula in propositional logic involve T, true, false, and other propositional variables and operators from the set, not, and, or implication and biconditional operations. Okay, so let's see the basic step. Once we have the basic component true, false, and S, where S is a propositional function variable, which we define them will form the formula. In other words, true, false, and this variable, propositional variable S, we just define they are will form formula. They are correct form. Okay, so we can define them in the basic step. And then for the recursive step, if E and F are well formed formula, then following these forms, they are all well formed formula. For example, we can use a particular E, not E, or E and F, E or F, or if E then F, and biconditional of EF. These forms are well formed formula. Okay, so in this case, we can use members from the basic step, T, F, or S, into this well-formed formula. Then we can create more propositional formulas into the set. Okay, so let's see how we can expand this set of well-formed formula. Because in the basic step, we already know that T, F, for example, PQ, this is atomic proposition, right? We cannot separate P and Q more to smaller part. So we call this atomic representation. Okay, PQ, TF are well-formed formula. Then following the recursive definition, we can write P or Q. P, if P, then F, or Q or F. Because you can replace PQTF into the recursive steps for these 5 different forms. Okay, so assume E and F are well-formed formula. So in the real example, we can replace EF by PQTF into this well-formed formula. Okay, so we can see P or Q, if P then F, P or F, Q or F, they are all well-formed formula. Okay, so this is the results of the first recursive step. Once we jump to the second recursive steps, we will have more elements into the well-formed set. For example, this one, and this one are all well-formed formula. So we can use these 3 terms into these 5 correct forms again. For example, we use P or Q as E, and Q and F as F into the previous definition of recursive step. So we will have, if P or Q, then Q and F. This is also a well-formed formula. Okay, and then we will have Q or P or Q. Okay, because where does this come from? Q is in the original definition of a basic step, right? And in the first recursive step, we know P or Q is true. So we can pretty sure Q or P or Q, this is well-formed formula. So we can replace this by E or F, okay? And then for if P then F, then true. Okay, so we know this is also will-form formula because if P then F, we can derive this by the first step of recursive step. And this is true by the basis step. Okay, so once we replace these two terms into E and F, then we will know this is correct will-form formula. Okay, so given any propositional function, you can see how they can derive using this definition of will-form formula. Okay, maybe you can derive them step by step, why they are will-form formula. Okay, so next you can verify PQ and or not and PQ. These are not will-form formula because you cannot derive from the basis step to recursive step to derive the following terms. Okay, so this is another recursive definition for will-form formula when we examine the correctness of propositional logic. Okay, next let's see another structures. For this part, we will introduce rooted tree. Okay, so let's see the definition of this particular structure, tree, especially rooted tree. Okay, the set of rooted tree where the rooted tree consists a set of vertices and containing a distinguished vertex which called root. Okay, so we have edges connecting this vertex to the roots. We can apply the recursive definition for such structure. Okay, so maybe we can see the example of rooted tree. We have a particular vertex root. Okay, so for the root, it's starting from the top. Okay, and then we have connecting edges to other vertices. Okay, once we can distinguish which vertex is root, then we can call this rooted tree. So we may have a lot of different forms of rooted tree. However, we can apply recursive definition how to create such rooted tree. So for basic step, there is a full, okay. For basic step, we have a single vertex R is a rooted tree. If we have only one single vertex, that could be a rooted tree because we can assign that vertex to be the root. Okay, and then for recursive step, suppose we have a different rooted trees, T1, T2 to Tn, which has the root R1, R2 to Rn respectively, and then we can connecting these rooted trees with an edge, connecting the root R1, R2 to Rn to the root. Okay, then by such manners, we can create another rooted tree. Okay, so let's see. For the basic step, we have only one vertex. We call that root of that rooted tree. Okay, and then we can consider this one as a rooted tree, T1, in the recursive step. Okay, once we consider this node as a rooted tree, then we can connect an edge from R1 to the root. Okay, this helps us to create another rooted tree. Okay, then we can also consider from the basic step, we have rooted tree 1, rooted tree 2. Okay, then we can connect edge from R1 and R2 to the root node. This helps us to create another rooted tree. So similarly, you can create a rooted tree with leaves of 3 leaves, 4 leaves, or more. Okay, so that we can create rooted trees by step 1. Following step 1, we have more candidates we can use because this is a rooted tree, this is a rooted tree. So if we consider This is the rooted tree from here, right? So we call the root of this rooted tree R2. And we also have the rooted tree from basis step. So the root of the basis step, we call that R1. So we can connect edges from R1, R2 to the root. Therefore, we can create another rooted tree. Okay, so in this case, you can see we have one rooted tree in basis step. We have 4 different trees in step 2. For step 1, then for step 2, we can composite all these rooted trees to create new trees. Okay, so you can see by this case, this rooted trees is from step 1. So if we call the root R1, then just add additional edges from R1 to R, then we can create another rooted tree. Of course, you can have different branches, just like step 1. Okay, so maybe we can have like 4 or 5 different branches that connecting to different rooted tree, T1, T2, or T3. Okay, so in this case, you can see, given any rooted trees, we can create the rooted trees using the recursive definition. Okay, by this rooted tree, by this recursively defined rooted trees, we can create all kinds of rooted trees that can follow basis step and recursive step to create such tree. Okay, is this okay? All right, so let me give you a tree example. So can anyone help me to build these trees by the recursive definition? So I will invite someone to draw the steps how to create such trees using basis step and recursive step. And I will give you 2 extra points. Anyone? All right, if no one wants to get points, then I will leave this as an exercise. You can practice by yourself because in the final exam, you might see the question like this, okay? Next, let's see the definition of full binary tree, okay? So the full binary tree is a very special or particular trees of rooted trees because we can see the definition, how we can create full binary trees using recursive definition. Okay, for basic step, there is a full binary tree consisting of only one single vertex R. So the basic step is exactly the same to the definition of rooted tree. We have only one vertex R as the root of full binary tree. For recursive step, okay, so we can tell the difference. If we have T1, T2 are disjoint full binary tree, then there is a full binary tree denoted by T1, T2 consisting root R together with edges connecting to T1 and T2. Okay, so you can see for the recursive steps, we only have 2 disjoint full binary tree, and we need to connect T1 and T2 to the root R. This gives us full binary tree because we only have 2 branches. We cannot have 2 more branches, such as 3 branches or 4 branches. We only have 2 branches, okay? And then for each steps, we need to connecting T1 and T2 to the root. Okay, so we call that full binary tree because we cannot have only one subtrees as T1 or T2. We need to have T1, T2 together to create next level of the tree. Okay, so let's see the example how we create full binary tree. In the basic step, we have only one vertex. This is also a full binary tree. Okay, then in the next step, we can use such trees as T1 and T2, and we can connect T1, T2 by additional edges from R1 and R2 to R. Okay, this helps us to develop another full binary tree in step 1. Okay, and that's the only tree we can create for step 1. Then for step 2, we have 2 different candidates because currently we have one vertex as full binary tree. And in this case, we have 3 vertices as the full binary tree. So for step 2, we can choose this tree as T1 and this tree as T2. We can also choose this tree as T1 and this tree as T2. Otherwise, we can choose both T1 and T2. The full binary tree are created in step 1. Okay, so you can see by step 2, we can grow the full binary tree to 3 additional trees. Okay, that's the definition of full binary tree. Next, we will see what is structural induction, because currently we have a lot of different recursive definitions, even recursively defined set, recursively defined functions, or recursively defined trees. Okay. Next, we will see how we can apply something like mathematical induction. We call that structural induction by this recursive defined set. Okay, so that's the definition of structural induction. To prove the property of the elements of recursively defined set, we use structural induction. Okay, so we also have 2 steps. Basic steps show that the results holds for all elements specified in the basic step of the recursive definition. Because previously we can see for full binary tree, we have a basic step to create the full binary tree, right? So for the structural induction, the basic step is to show that we have such property holds for all elements from basic step. Okay, so in this case, if we want to prove some properties of full binary tree, the first step is to make sure the property holds for vertex R, because the vertex R is the elements in the basic step. So if we want to apply structural induction to prove some properties of full binary tree, then for basic step in the structural induction, we need to prove the property holds for this single vertex R. Okay, and then let's see what is recursive step. We need to show that if the statement is true for each element used to construct new elements in the recursive step, then the results also holds for those new elements. Okay, so maybe we can relate it to inductive hypothesis. From previously, we have mathematical inductions. We assume P of K is true, then we further extend to prove that P of K plus 1 is true. Okay, so what is the inductive hypothesis of structural induction? Because we assume the statement or the property is true for all these elements used to construct new elements in the recursive step. If the element used to construct new elements, we have such property holds for these elements, then we need to prove that the results also holds for new elements. Okay, so let's see the example. Okay, so we have seen this recursively defined set before, right? We have a set S. If 3 in S, then if X and Y also in S, X plus Y also in S. Okay, so previously we have seen this definition, right? This one, okay. Once we have basic step, 3 in the set S, then for recursive step, X, Y in S and X plus Y also in S. So we can apply 3 as x and y. So x plus y is also in S. Therefore, 6 is also in S. Then we will have 6 and 3. So 6 plus 3, 9, also in S. Okay, so let's see for this example. Once we have such set S, then we can prove that this set is the set of all positive integers that are multiples of 3. Okay, because we have seen 3, 6, 9, 12. We can expand this set, becomes larger and larger, but all elements are multiples of 3. Okay, so in this example, we need to prove once we have a spatial set S based on the recursive definition, then we need to prove the set is equal to the set of all positive integers that are multiples of 3. Okay, so if you remember how to prove equality of two sets, the basic principle is to prove that once we have two different sets A and B, we want to prove A equals B, then we can prove that A is a subset of B and B is also a subset of A. Then we can say that A equals B. Okay, so here we will apply mathematical induction and structural induction for this problem. Next, let's see how we prove both sets are equal. Okay, so we already have the definition of the set S, right? Because we have the recursive definition for the set S. Next, let's define, we have another set A. A are the set of all positive integers, which are multiples of 3. If they are multiples of 3, we can also say that it is divisible by 3. Okay, now we have two different sets, S and A. Next, we need to show that if two sets are equal, then A is a subset of S or S is a subset of A. Okay, so next let's see how we prove that A is a subset of S. Okay, remember the definition of subset. How we prove that A is a subset of S? If the elements in A is also in the set S, then we can call A is a subset of S. Okay, this is how we prove A is a subset of S. Okay, so we already know that A is a subset of all positive integers that is divisible by 3 or multiples of 3. So we claim the propositional function P of n to be the statement 3n belongs to S. Once it is multiple of 3 or it is divisible by 3, then we can write all elements in A to be 3n. Okay, then we need to prove A is a subset of S. So we need to make sure all elements in A also in the set S. So we need to claim 3n also in the set S. Okay, this is the propositional function we need to prove. Then let's jump to basic step, how we apply mathematical induction to prove that 3n belongs to S. Okay, because for basic step starting point, we set 1. So 3 times 1 equals 3. Okay, this gives us 3 is also in the set S because we already know this from the basic step of the recursive definition of the set S. Okay, so 3 in S, basic step is no problem. Then let's see inductive step. Assume PK is true, then we need to prove that P of K plus 1 is also true. Okay, so if PK is true, then we know 3K is in S. Okay, then based on this inductive hypothesis, we need to prove that P of K plus 1 is also in S. So P of K plus 1 will be 3 times K plus 1. Okay, 3 times K plus 1. we can separate to 3k plus 3. Okay, then based on inductive hypothesis, we already know 3k is in S. Then 3 is also in S from the basic step of the definition of S. So if x and y are in S, then x plus y is also in S. Okay, so 3k plus 3 is also in S. This is true. So we complete the step to prove that A is a subset of S. Okay, next let's see how we prove S is a subset of A. Okay, so we already know that S is created by the recursive definition. So let's see for basic step. Basic step, we have the only element 3 in S. Okay, so S is a multiple of 3. This number 3, it is also divisible by 3 because 3 equals 3 times 1. Okay, so we can see actually this element is a multiple of 3. So this element in S and it is also in A. So basic step is no problem. Next, let's see inductive hypothesis. Okay, for inductive hypothesis, we know the definition. If we assume X and Y also in S, then we need to X plus Y will be in S. Okay, so in this case, we can see if X and Y are both in A, because if X and Y in S, then it will be a multiple of 3. Okay, so if we assume X and Y in A, this is our inductive hypothesis. We assume X and Y in A, then both X and Y are divisible by 3. This is by inductive hypothesis. Then we can show that X plus Y is also divisible by 3. Because if X and Y are divisible by 3, then X plus Y, we also have the common factor 3. Therefore, X plus Y is also divisible by 3. Okay, so maybe we can relate this example to the definition of structural induction. So let's see how we connect the definition to what we have done for previous example. In the recursive step, we need to show that, okay, let's from the basic step. Okay, so we need to show that the result holds for all elements specified in the basic step of recursive definition. So from the previous example, the recursive defined function S, we only have one element 3. Okay, so for basic step, we need to verify the element 3 also follow the property. It is in the set A. Okay, so that will be easy. Next, in the recursive step, let's see the inductive hypothesis. If the statement is true for each element used to construct the new elements in the recursive step. So from the previous example, we know that we use X and Y to construct the new elements X plus Y. Okay, so in this case, we assume the statement is true for each element to construct the new elements in the recursive step. So we assume X and Y, which follows the properties. For our examples, X and Y, if it is in S, then it is also in A. If we assume this is true, so that's our inductive hypothesis. Then we need to prove, based on this inductive hypothesis, we need to prove that if it constructs new elements in the recursive step, in our example is X plus Y, then the result also holds for the new element X plus Y. Okay, so let's go back to our example. Once we assume X and Y, because X and Y are elements used to construct the new elements, so we assume the property holds for X and Y. So we assume X and Y are divisible by 3. This is our inductive hypothesis. Then we need to verify if we use x and y to construct the new elements will be x plus y. Then we need to prove that x plus y is also follow the properties. It is divisible by 3. Okay, so the proof is very easy because once x and y are divisible by 3, then we have the factors 3 we can separate from x and y. Therefore, x plus y, we can also have the common factor 3 times something. Okay, so this gives us x plus y is also divisible by 3. All right, so let's see. This is how structural induction applies. Once we can apply structural induction to basic step, the elements is created by basic step of the recursive definition, then we can prove all elements follow the properties. That's how we complete the basic step. For recursive step, we assume the inductive hypothesis is the elements used to construct new elements follows the properties. That's our inductive hypothesis. Then we need to prove that new elements also follow the properties. That's the recursive step. Okay, so I hope you can review this problem carefully when you go home, because I think this is a very good example. It follows mathematical induction and structural induction. We need to prove if A is a subset of S and S is also a subset of A. 好，到这边可以吗？知道我们在讲什么吗？好，那个大家表情都很难过哦。好，好，那我们就用中文稍微再讲一下哦。好，就是实际上我们接下来要用的 structural induction， 好，它就是一个怎么样证明结构化东西的数学归纳法。所以我们前面已经有定义了很多结构化的东西，不论是结构化的函数或结构化的集合。好，那如果我们要证明这一种以 recursive define 的形式所产生的结构或者是函数的特性的时候，好，那这一类的数学归纳法呢，我们就称为结构化的数学归纳法。那结构化数学归纳法怎么去证明结构化的定义所产生出来东西的性质呢？好，我们还是用 basic step 跟 recursive step。好，那 basic step 呢，就是证明在结构化的在 recursive 的定义里面的 basic step 那些 element 它会有这个性质。好，这个就是 structural induction 的 basic step 要做的事情，它跟 recursive definition 的东西是对应的。好，我们前面呢有 recursive define 的 basic step， 也有 recursive define 的 recursive step。好，那我们现在要把这个结构化的数学归纳法的这两步对应到 recursive define 的 basic step 跟 recursive step。好，所以我们这边要做的第一件事情呢，就是我先确保这边的 basic step， 我可以证明在刚刚 recursive definition 的 basic step 的 elements， 它有这些特性。好，所以我们刚刚做的证明的第一件事情呢，就是在 recursive definition 里面，这个 S 的集合，它的 recursive definition 的 basic step 是不是只有3这个元素而已？好，我们说它的 basic step 只有3嘛。好，在 recursive step 里面，我们说假设 x 跟 y 都在 S，x 加 y 也在 S， 这个是 recursive step。那 basic step 呢，只有3在这个集合 S 里面。所以我们在做结构化的数学归纳法的时候，我只要证明在这个 recursive definition 的 basic step， 也就是3这个元素，只要3这个元素能够证明符合我要证明的性质，那我的结构化的数学归纳法的 basic step 就结束了。好，了解吧？好，所以我们要证明的是，假设3在 S 这个集合里，3也在 A 这个集合里。那3在 A 这个集合里的意思是什么呢？就是3这个数是3的倍数或是可以被3整除。那这个当然显而易见就是成立嘛。好，所以我们就先证明了在 S 这个集合 recursive define 的结构里面，它的 basic step 的元素，这个元素有符合我们想要证明的特性。 好，这个就是结构化数学归纳法的 basic step。好，那结构化的数学归纳法的 inductive step 是什么呢？好，就是我们说在原本的 recursive define 的这个集合里面，它的 inductive step 是告诉我们，假设我用 x 跟 y， 它都在 S 里面，那 x 加 y 也会在 S 里面，所以这个里面有分两个东西哦。好，第一个呢是 x 跟 y 在 S 里面。那 x 加 y 是一个新的元素，是我们借由 inductive step 所产生出来的新的元素。这个东西是定义在原本的 recursive define 的 set S 里面的。好，那我们现在要用结构化数学归纳法证明的事情，要证明说，现在我用 x 跟 y 来产生新的元素 S 的时候，那我要先假设我的 inductive hypothesis 就是我用 x 跟 y 来产生它。那 x、y 如果符合我们的特性，那我产生出来新的元素 x 加 y 也会符合我们的特性。那我们的假设就是，假设 x 跟 y 是在 inductive step 我们的 recursive define 的 set 里面所使用的元素，那我的 inductive step 就是 x 跟 y 有符合我们题目的特性。那我们题目特性是什么呢？就是它能够是3的倍数或是被3整除。好，所以我们就假设 x 是可以被3整除 ，y 也可以被3整除。好，那我们接下来有了这个 inductive hypothesis 之后，我们就看看它所 create 的新的元素。这个 create 的新的元素呢，是在原本 recursive define 的 set 里面所产生的这个 inductive step 的这个 x 加 y 的这个新的元素。好，那我们要证明这个新的元素也会符合这个特性。那这个证明就很简单啦，因为 x 能够被3整除 ，y 也能被3整除，那当然 x 加 y 也能被3整除。好，因为它能够写成3的倍数的话 ，x 可以写成3乘上 k，y 可以写上3乘上 t， 那两个加起来就是3括号 k 加 t。好，那当然 x 加 y 也有3的这个因素存在，因此它可以被3整除。好，那这个就是我们用这个简单的例子来告诉大家，怎么样来用 structural induction 来证明 recursive define 的 set。好，这件事情。好，那我们再重新看一下这个句子哦。好，这个句子看起来有点饶舌。它告诉我们，假设我们的 statement 是 true for each element used to construct new elements in the recursive step。那在我们刚刚的例子里面 ，x 跟 y 就是我们的 element， 用这些 element 去 construct new element x plus y。那我们要假设这个 statement 是 true for each element used to construct the new element。所以 x 跟 y 这两个 element 用它来产生新的 element 的时候，我们先假设 x 跟 y 它有符合这样的特性。好，然后呢，我们要证明这个特性呢也会在新的元素上面成立。好，所以我们的第一步呢是我们的 inductive hypothesis。接下来我要证明在新的元素上它也会符合我要证明的这个特性，那我就完成了 structural induction。好，所以你可以发现 structural induction 跟 recursive define set 或是 recursive definition 的 basic step 还有 recursive step 这两个步骤是很紧密的绑在一起的。好，那我们用这个结构化数学归纳法的 basic step 来证明我们 recursive define 的 basic step 的元素都符合满足这个特性。那接下来呢，我的 recursive step 在数学归纳法里面，我也在这一步去验证在 recursive define set 的 recursive step 里面所产生的新的元素，它也会符合这样的特性。好，所以这两步跟我们的 recursive definition 的这两步是绑在一起做证明的。好，这样可以吧？好 ，All right. We have one more example to help you verify if you can apply structural induction successfully. Okay, so next let's introduce two different definitions for tree. The first one is the height of full binary tree. Okay, so it's also a recursive definition. So let's see, for basic step, the height of full binary tree T consisting only one rooted vertex R, and we define the height of that tree is 0. Once we have only one vertex R, it's also a full binary tree, and we define the height of such tree is 0. This is the basic step. And then for recursive step, if we have T1, T2 as the 4 binary tree, then we connecting T1, T2 to the root R by 2 additional vertex edges, okay? So we define the height of that tree, T, will be 1 plus max of height 1 and height 2. Okay, so let me give you an example how to consider the height of a four binary tree. Okay, so if we have a binary tree like this, okay, so how we calculate the height of this 4 binary tree? Because if we have only one vertex, this is the root of 4 binary tree, then the height is 0. Okay, then let's see if this is T1, this is T2. Okay, so let's see what is the height of T1. 0, right? Because it contains only one root. Okay, and the height of T2 is 1 because we consider the height of this tree. If we have only one root is 0, then the height of T2 is 1. Okay, so the height of the tree is 1 plus max of 0 and 1. Okay, so that will be 2. Okay, so let me give you another example. Okay, so this is height 0. This is height 1. This is height 2. Okay, because we consider the height, this is height 1 because we have only one branches of subtrees, and we can consider this is height 1, this is height 2. Okay, this is height 0. Okay, so for this case, we can define the height of the 4 binary tree to be height 2. Okay, so it's easy to calculate the height of the tree directly. However, we can also calculate the height of the tree using the recursive definitions following the basic step and recursive step. Okay, so that's the recursive definition to calculate the height of a 4 binary tree. Next, let's see the definition, how to calculate the total number of vertices in a 4 binary tree. So we use n of capital T. So capital T representing the tree, and n of T means the total vertex in the tree. For basic step, once we have only one vertex, the root, then n of T equals 1. For recursive step, if we have two subtrees, T1 and T2, then the total vertex will be 1 plus the number of vertices of T1 and total vertex of T2. So this is total vertex T1, total vertex of T2. So this one means the vertex of root. Okay, so the total number of vertices will be 1 plus the number of T1 and number of T2. Okay, I think this is more intuitive to calculate the total number of vertices. Actually, you can calculate the vertex by yourself, 1, 2, 3, 4, 5. Okay, so, but we can still follow the recursive definition to calculate the number of a given 4 binary tree T. Okay, next let's apply structural induction to verify the properties. It's also a theorem. If T is a 4 binary tree, then the number of 4 binary tree is less than or equal to 2 to the power of h of t plus 1 minus 1. Okay, so this is a theorem to tell us the upper bound of the number of vertices of a full binary tree actually is related or highly related to the height of the tree. Okay, next let's see how we apply structural induction to prove the property of the number of vertices of a given full binary tree T. Okay, so for basic step, remember we need to verify the elements based on the recursive definition. In the basic step, it follows the condition. Okay, so we can see for full binary tree, if you remember the definition of full binary tree, okay, so this is the definition of full binary tree. For basic step, we have only one single vertex R. Okay, so we need to verify, once we have only one single vertex R, it follows the property n of t less than 2 to the power of h of t minus 1 minus 1. Okay, so let's verify the first step if this element's single vertex R follows that property. Okay, so we can see this is very easy because once we have only one vertex R, then n of t is 1 and h of t is 0, following the previous definition of height t. Okay, then we can see n of t is 1. 1 is less than or equal to 2 to the power of 0 plus 1 minus 1, which is 1. Okay, so to apply the structural induction, we just verify the elements of full binary tree in the basic step. It follows the properties. Okay, next let's see for recursive step. Okay, let's see what is the inductive hypothesis. Assume we have T1, T2 as the left and right subtrees, then it follows the properties because we use T1 and T2 create new elements to create new full binary trees in the recursive step. So for inductive hypothesis, we assume this property is correct for T1 and T2. Therefore, we can write n of T1 less than or equal to 2 to the power of n of T1 plus 1 minus 1. Okay, it also holds for T2. Okay, so we have two such inequality holds as our inductive hypothesis. Next, let's calculate n of t. Actually, the new tree T is created by T1, T2. Then we need to verify this property is also holds for new element T. Okay, so let's see if it follows the property. So based on the definition, n of t, we know that it's 1 plus n of t1 plus n of t2. That's from the recursive step of the definition of total number of the tree T. Okay, and then we can apply the inductive hypothesis because n of t1 is less than or equal to this number, and n of t2 is less than or equal to this number. Okay, so we just apply the inductive hypothesis. Then we can rewrite this equation a little bit because if we have this one plus this one plus this one, we have minus 1, and plus 1 here. So we can erase these two terms. We have only minus 1 left. Okay, so next, let's see. We have these terms and these terms. Okay, so we can assume one of these terms is larger than the others. So we can write the summation of these two terms are less than or smaller to, less than or equals to max of these two terms. Okay, times 2. Because we can choose the max number from these two numbers. Then if we use 2 times the max numbers, so the original summation of these two terms will be less than or equals to when we apply the max operation of these two numbers. Okay, and the max of these two numbers, we can rewrite the max operations to the power of h of t1 and h of t2. Okay, so that's is the definition of height. If you remember, the height is 1 plus max ht1 and ht2. That will be the height of tree T. Okay, so you can see once we have max of ht1 and ht2 plus 1, that will be the recursive definition in the height of tree T. So we can write h of t. Okay, so therefore we have 2 times 2 to the power of ht minus 1. So this gives us 2 to the power of h of t plus 1 minus 1. Okay, so we just proved that n of t, which is less than or equal to 2 to the power of h of t plus 1 minus 1. Okay, I think the calculation is very easy. The important thing is how to apply inductive hypothesis. Okay, so once we have the original numbers in the inductive hypothesis, in the recursive step of full binary tree, okay, so let's go back to the recursive step of full binary tree. Once we have T1, T2, we use T1, T2 to create new elements, T, okay? And for inductive hypothesis, we assume T1 and T2 follow the properties. Then we prove that the new element T also follow the properties. Okay, so that's how we apply structural induction, because in this case, we use T1 and T2 in the recursive step of structural induction, and we need to provide the inductive hypothesis. Therefore, we can derive these two inequalities. Okay, then following these basic calculations, we can prove that n of t also follows the property. The number is less than or equal to 2 to the power of height of t plus 1 minus 1. All right, next let's jump to the topic, generalized induction. Okay, this will be the last topic of this section. Generalized inductions is used to prove the results of set. Okay, especially they have something is called Weyl ordering properties. Okay, so let's see what is Weyl ordering properties. If we have an ordering on order pairs, okay, so these order pairs we call that x1 and y1, and we want to compare the ordering because x1, y1 is less than or equal to x2 and y2. So we can compare the number or real numbers of x1 and x2, y1 and y2, but we cannot compare a pair of numbers. Okay, so here we have the definition, how we compare the order or sequence, which is larger, which is smaller. Okay, we call this lexicographics ordering. Okay, so the definition is if we have two pairs, x1, y1, x2, y2, then when we specify x1, y1 is less than or equal to x2 and y2, we follow the condition x1 less than x2. If the first element is less than x1 is less than x2, this is the first element. We compare the first element first. Or if they are equal, x1 equals x2, but y1 less than y2, then we can specify the first pair is less than or equal to the second pair. Okay, so because we cannot compare a pair of numbers to another pair of numbers, okay, so this is how we compare. Once we need to have the order n times n, we have such order pairs. This is how we compare their orders. We call this lexicographics orders. Okay, next, let's see more examples how we apply generalized inductions. Because we have mentioned that general inductions is usually apply to set other than integers if we want to consider its lexicographic ordering. Okay, let's see this example. Suppose we have AMN defines for the order pairs MN. Okay, and A00 is 0, and the term AMN, we have two different definitions. If N is 0 and M is larger than 0, then we can use the previous term to define AMN terms, okay, because it will be equal to AM minus 1, N plus 1. Once N is larger than 0, then this terms equals AM M minus 1 plus N. Okay, so let's see, for this case, we have the order pair M and N. Okay, then we can use these terms to define different terms of using A, M, N. Okay, so next, let's show that the term AMN equals M plus N times M plus 1 divided by 2. Okay, so you can relate this example to sequence, right? Because we also derive the formula for AN terms in the sequence. We don't like to use previous terms. Once we need to use previous terms to derive AMN, then it's difficult because if we want to derive A 100, 100, then you need to calculate maybe all previous terms, or 99, 100, or A 199. Okay, but if we can derive the equation or formula for AMN terms directly, then we don't use previous terms. Once we know the index M and N, then we can derive the AMN terms directly. Okay, so this is very similar to the problems in the sequence section. Okay, next let's see how we apply generalized inductions using lexical ordering. Okay, for basic step, let's see if this equation is correct. A0, 0. Okay, so we know M is 0 and N is also 0. Okay, so follow the equation. If N is 0 and M is also 0, then 0 plus 0 times 0 plus 1 divided by 2, okay, the results will be 0. And we know A00 is 0. It's the initial condition. Okay, so for basic step, we know A00 equals 0 is right. Okay, next, let's see inductive step. Okay, assume we have another term, A, M prime, and M prime. Okay, it follows the equation M prime plus M prime times M prime plus 1 divided by 2. Okay, because M prime and M prime is less than Mn in the lexicographics ordering. Okay, so that's our inductive hypothesis. If the order is less than Mn, then it follows this formula. Okay, next, let's see what happens if N equals 0 or N is larger than 0. Okay, so by inductive hypothesis, we know that M minus 1 N is less than Mn in the lexicographics ordering. Okay, so therefore we can conclude that AMN follow the definition. It's AM minus 1 N plus 1. Okay, because we assume N is 0, so we use the first equation. Okay, so this gives us M minus 1 plus N times M plus 1 divided by 2 plus 1. okay, because we know what is this. The graphics ordering of these terms is smaller than AMN, right? If the lexicographics ordering is less than AMN, then it follows our inductive hypothesis. We can use the equation directly. Okay, then we assume n equals 0. So by this formula, if n equals 0, then we will apply the first equation. Okay, so am minus 1n, okay, will be n minus 1 plus n times n plus 1 divided by 2. Okay, then we have plus 1 in the end. Okay, so this gives us n plus n times n plus 1 divided by 2. That verify our equation is correct. On the other hand, if n is larger than 0, okay, so let's see, we have, if n larger than 0, we need to use equation 2, right? But for equation 2, m and n minus 1, this terms is also less than mn in the lexicographics ordering because x1 equals x1 and y1 is less than y2. Okay, so this paired numbers, its lexicographic ordering is less than mn. Okay, so if it is less than, then we can follow the inductive hypothesis to apply the equation directly. Okay, so m and m minus 1. Okay, in this case, we have m plus n minus 1 times n divided by 2 and plus n, right? So in this case, we can also rewrite this equation to m plus n times n plus 1 divided by 2. This is also verify our equation is correct. Okay, so you can see this calculation is very easy. However, it follows the where ordering properties. Once we have order pairs x1, y1 and x2, y2, and we need to prove some properties of this where ordering properties, we can use generalized inductions following this lexicographics ordering to prove some properties of these terms. All right, let's see the homework assignment of this chapter. So today, maybe we can set the submission date. Okay, today is May 8th. Okay, so our submission date will be right. I hope you can practice the homework assignment by these 3 sections. So maybe your concept of mathematical induction, strong induction, and structural induction, you can clearly identify the difference of all these methods. But just like we have mentioned in section 5.1, actually they are all equivalent. However, maybe for some questions or homework assignment, one method is easier than the others. So you can choose the easier one to derive your answer. OK， 好，那我们最后看看同学们对这个章节有没有什么问题？好，没有的话 ，see you next week.